Design of experiments begins with a surprisingly practical complaint. Experiments are expensive, slow, noisy, and often politically loaded. If we change one factor, run a trial, change another factor, and hope intuition catches the pattern, we spend a lot of effort learning too little. DMAIC is the statistical art of choosing the trials before the data arrive, so that variation becomes information instead of confusion. Its promise is not that experiments become effortless. Its promise is that every run has a reason, and the reasons can be audited. The core question is not, did one run look better than another? The core question is, which input factors change the response? How large are those effects? Do factors interact? And how uncertain are our conclusions? A factor might be temperature, catalyst level, feed rate, training script, fertilizer, voltage, or algorithm setting. A response might be yield, purity, conversion, cycle time, cost, defect rate, customer wait time, or taste score. DMAIC forces us to name the response before we optimize, because an experiment without a response is only activity. DMAIC sits directly on statistical testing theory. We imagine a response model. Y equals signal plus random error. In the simplest linear experiment, y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 12 times x1, x2 plus epsilon. The epsilon term is the noise, measurement error, material variation, human variation, or any uncontrolled influence that remains after the design. The design matrix is the table of chosen factor settings, and the model matrix is what turns that table into estimable coefficients. Testing enters when we ask whether an estimated effect is large compared with its uncertainty. A null hypothesis might say beta 1 equals 0. Factor 1 has no effect in this model. The estimate beta hat 1 has a standard error. The ratio estimate over standard error becomes a t-statistic, and the p-value asks how extreme that statistic would be if the null model were true. Confidence intervals show effect size plus uncertainty, which is usually more useful than a yes or no label. Power is the other side of the coin. The probability that the design will detect an effect of a practically important size. ANOVA, analysis of variance, is the bookkeeping engine behind many classical designs. It decomposes total response variation into variation explained by factors, interactions, blocks, and residual error. The F-statistic compares mean square for a term against mean square error. If the factor variation is much larger than residual noise, the model says the factor is unlikely to be inert. ANOVA is not magic. It is variance accounting under model assumptions. The sums of squares are geometric. Project the response vector onto model subspaces, then ask how much length each term explains. Those assumptions matter. The usual linear model analysis expects independent errors, roughly constant variance, and residuals that are not wildly non-normal when sample sizes are small. Randomization supports independence by breaking hidden time patterns. Replication estimates pure experimental noise. Blocking removes known nuisance variation, such as day, batch, operator, machine, supplier lot, or field location. Good design is not just more data. It is data whose uncertainty can be trusted. If the measurement system is unstable, even a beautiful design gives beautifully misleading numbers. The enemy of DMAIC is one factor at a time experimentation. Suppose temperature and pressure both affect yield, and their combination matters. If we vary temperature while pressure is fixed, then vary pressure while temperature is fixed, we may never see the interaction. Worse, we learn only along two thin slices of the input space. A factorial design changes factors together in a planned pattern so main effects and interactions become visible. The paradox is that changing several things at once can be clearer than changing one thing at a time when the changes are orthogonal and planned. A two-level factorial design is the cleanest gateway. Put each factor at a low level and a high level. With 3 factors, the full design has 2 cubed, or 8 corner runs. The average response at high temperature minus the average response at low temperature estimates the temperature effect. The same contrast idea estimates pressure, catalyst, and interactions. The geometry is beautiful. Effects are directions across the cube. Coding levels, as -1 and +1 makes the columns orthogonal, so each coefficient is estimated without borrowing information from the others. Interactions are where DMAIC earns its keep. If factor A helps only when factor B is high, the effect of A depends on B. On a plot, interaction means non-parallel lines. In business language, An interaction says that best practices are conditional. A training script may help new agents, but slow experienced agents. A fertilizer may help in dry soil, but hurt in wet soil. Dewey gives that conditional reality a mathematical name. Ignoring interaction can make a strong factor look weak, or make a harmful combination look safe. Full factorial designs can grow quickly. 5 two-level factors require 32 runs. 10 factors require 1,024 runs. Fractional factorial designs deliberately run a carefully chosen fraction of the cube. The price is aliasing. Some effects are mathematically blended with other effects. The benefit is screening. With far fewer runs, we can identify the small set of factors likely to matter. This works because many systems are sparse. Most factors in high-order interactions are often negligible. In screening, we are trying to buy focus, not final truth. Resolution is the language of aliasing risk. A resolution 3 design can estimate main effects, but main effects may be aliased with two-factor interactions. Resolution 4 separates main effects from two-factor interactions, but two-factor interactions can be aliased with each other. Resolution 5 is stronger again. The business translation is simple. A fractional design is not a shortcut without cost. It is an explicit trade between budget and ambiguity. Foldover experiments can later break aliases by adding a complementary set of runs. After screening, we often move from discovery to optimization. Response surface methodology fits a local empirical model, often with linear, interaction, and quadratic terms. Quadratic surface can show curvature, ridges, and optima. Central composite and Box-Bankin designs add center points and axial or balance points so the model can estimate curvature. Now, the goal is not only which factors matter. It becomes where should we set them. Center points are especially useful because they give a quick test for curvature and a repeated estimate near the current operating condition. Optimization under uncertainty is not just chasing the highest predicted mean. We also care about robustness. Taguchi-style quality engineering emphasized making performance insensitive to noise factors. In modern language, we might optimize expected response, variance, defect probability, cost, and operating constraints together. A slightly lower mean with much lower variability may beat a fragile optimum that fails whenever humidity, raw material, or user behavior shifts. This is where engineering judgment returns. Statistics proposes a region, but constraints and failure modes decide whether it is usable. The business roots of Dewey are broader than lean alone. Fisher developed experimental design for agriculture, where randomized blocks and replication made field trials credible. Industrial statisticians, such as Box, Hunter, and Taguchi, brought designed experiments into chemical processes, manufacturing, and quality improvement. Lean focuses on flow and waste reduction. Six Sigma focuses on variation reduction and statistical process improvement. In Lean Six Sigma, Dewey often appears in the improve phase of DMAIC. Define, measure, analyze, improve, control. So it is fair to connect Dewey with lean engineering practice, but historically it comes from experimental statistics and industrial quality more directly. A practical Dewey begins with the problem statement. What decision will change after this experiment? Choose one primary response, or explicitly define a multi-response objective. Choose controllable factors, nuisance factors, safe ranges, and forbidden combinations. Decide whether the experiment is for screening, modeling, or confirmation. Estimate noise and practical effect size. Then choose a design with enough power to see effects that matter, not merely effects that are mathematically possible. Also decide who owns the run sheet, because execution discipline is part of the statistics. Consider coffee extraction as a compact example. Factors might be grind size, water temperature, brew ratio, and time. Responses might be extraction yield, bitterness score, and preference rating. A naive sequence changes grind, then temperature, then time. A factorial or fractional factorial design samples combinations. It can reveal that high temperature is good only with coarse grind, or that longer time helps extraction, but hurts preference beyond a threshold. The final recommendation might be a recipe range: coarse grind, moderate temperature, and time below the bitterness knee. Consider polymer curing. Temperature, catalyst percentage, humidity, and cure time influence strength and defects. Batches differ, and ovens may have zones. A blocked design can compare settings within each batch or oven day, protecting conclusions from nuisance variation. Replication estimates real process noise. After screening finds temperature and catalyst as dominant, A response surface design can map strength versus defect rate and find an operating window, not just a single lucky recipe. Contour plot can then show engineers where strength is high while defect probability remains below the customer limit. In service operations, DMAIC still applies, though ethics and logistics matter. A call center might test greeting script, routing rule, staffing threshold, and follow-up message. Responses include handle time, resolution rate, customer satisfaction, and repeat contacts. Randomization must avoid unfair treatment, and blocking by time of day or team can prevent calendar effects from masquerading as treatment effects. The same mathematics applies, but the design must respect people. In digital products, this becomes A/B testing and multivariate testing, with the added complication that users can influence each other and behavior changes over time. Analysis should be visual before it becomes ceremonial. Plot the design matrix, plot main effects, plot interactions, plot residuals versus fitted values, and run order. Check whether one dramatic point is driving the story. Look at confidence intervals and prediction intervals. Ask whether effects are practically meaningful, not only statistically detectable. DMAIC is a way to become less fooled, not a machine for producing p-values. If the plots and the table disagree emotionally, slow down and understand why before announcing the result. Confirmation is part of the design, not an afterthought. After selecting a setting, run confirmation trials at the chosen conditions, preferably on new material, a new day, or a realistic operating context. Compare observed performance with the model prediction interval. If the result misses badly, the model taught you something. The assumed region, factors, noise structure, or measurement system may be incomplete. A failed confirmation is not embarrassing if it prevents a bad process change from being scaled. Sample size deserves its own sober moment. More runs reduce standard errors, but power depends on noise, effect size, alpha level, model complexity, and how the runs are allocated. Replicates at center points answer different questions than extra corner runs. Repeating the whole design on another day answers a different question again. The design should match the risk. Screening can tolerate ambiguity, but a costly launch needs stronger evidence. Missing data and failed runs should be planned for, not treated as clerical annoyances. If a reactor run fails, if a participant drops out, or if a sensor saturates, the design can lose balance and some contrasts become less clean. A good protocol defines rerun rules before the result is known, because rerunning only disappointing trials quietly turns an experiment into wishful editing. There is also a sequential philosophy behind good DMAIC. Rarely should one giant experiment answer everything. A smarter path is often screening, then focus modeling, then confirmation. Each stage spends information from the previous stage. That is why DMAIC belongs naturally in engineering improvement. Learn broadly, narrow intelligently, optimize locally, and validate under real conditions. The workflow is cyclical. Define the decision. Map factors, responses, constraints, and risks. Choose a design. Randomize, block, and replicate. Run carefully. Fit the model. Test effects. Diagnose residuals. Interpret interactions. Optimize with constraints. Confirm. Then standardize the process and monitor it. The control step matters because an experiment creates knowledge, but operations create value. When the process drifts, the model is no longer a trophy. It becomes a hypothesis that must be checked again. The deepest lesson is that DMAIC changes the unit of thinking. We stop asking, what happened in this trial? We ask, what pattern of trials will separate signal from noise, reveal interactions, estimate uncertainty, and support a decision? That is why design of experiments is not just a statistical chapter. It is a strategy for learning faster when reality is noisy, budgets are finite, and decisions cannot wait forever. The best experiments feel almost unfair afterward, because the answer seems obvious only after the design made it visible.